Hello, Mr. Sorrentino here again, presenting another one of the videos from Math 31, which in this one is going to deal with section 3.4, solving rational equations and radical equations. So rational equations are ones like you see here in example 1, where I have expressions involving a variable and the denominator, recognizing that when we solve an equation, we want x or whatever the variable is in the numerator alone on one side. And we're going to deal with radical equations, which means we're going to have solve equations where I have the variable underneath of typically a square root sign, although they could be other roots as well, but we're going to focus our attention mainly on square roots for this course. So these two types of equations, your rational equations and your radical equations, are ones that produce possibility for extraneous solutions. I had mentioned this in passing in another one or two of these videos before this one. An extraneous solution is a solution to an equation where I do everything algebraically correct, but either because of the circumstance I'm presented with or any other things I may have to have assumed as I went through the process of solving the problem, just in the end produces an answer that just doesn't make sense to the context of the problem. So it's actually just an extra solution. I just disregard it once I realize it doesn't make any sense. These two types of equations are noted for having those quite a bit. And we can usually recognize them pretty easily once you get the idea of handling it. So let's take a look at, these types of equations. What can possibly produce the extraneous solutions, and how do we go about, solving these equations? When we solve rational equations, the primary principle that we're going to be using is a procedure known as cross multiplication. I mentioned this also before in a previous lesson. But when I'm using cross multiplication with rational equations, which basically means if I have an equation where I have a fraction equal to another fraction, that's important. A single fraction on the left of the equal sign equaling a single fraction on the right of the equal sign, then this is also true. I could multiply across the equal sign in a crisscross fashion. So I could say as a result of this, AD would equal BC. Now when I go through and do the procedure for this, A, B, C, and D could have one or two or even more terms in it. So I have to be aware of that as I do it. So the first one, I do have a single fraction on the left, I have a single fraction on the right. It's already set up to do cross multiplication. So if I wanted to solve A, I would do 2x times x plus 1, and that would equal 5 times x plus 7. One of the first things I want to do when I have a situation where I have x's in the denominators is get them out of the denominator when I'm trying to solve them. And cross multiplication allows for that to happen. Now I want to solve this equation, which means I'm going to need to do some simplifying. On the left, I'm going to distribute a 2x, so I'm going to have 2x squared plus 2x. On the right, I'm going to have 5x plus 35. Now we can see that this is a quadratic equation. I do have a degree 2, and it's a non-basic one because I also have x terms in here that are going to stick around. They're not going to cancel out with anything. At this point, I would have to make a decision, which method do I eventually want to use? Do I want to use factoring? Do I want to use completing the square, or do I want to use the quadratic formula? Now, under a lot of circumstances, when you're doing these equations, you could expect rational solutions, and we're expecting real number solutions. So another thing that they don't always say outright, when I'm solving rational equations and radical equations, I am solving them for real numbers, whereas with quadratics in general, it is possible for me to solve them for any number, real or non-real. So I'm just going to choose to use the quadratic formula for this. So I'm going to get this equation set equal to 0. So I'm going to subtract 5x from both sides, which will give me a minus 3x. I'm also going to subtract that 35. And using the quadratic formula, x is going to equal negative 3 plus or minus the square root of negative 3 squared minus 4 times 2 times a negative 35 all over 2 times 2. So 3 plus or minus the square root of negative 3 squared plus 4, minus 4 times 2 times negative 35 becomes a 289 all over 4. The square root of 289 is 17, so I'm going to have 3 plus or minus 17 over 4. 3 plus 17 is 20, divided by 4 is 5. 3 minus 17 is a negative 14. And a negative 14 divided by 4 is a negative 3.5. Now, as we start doing this more and more frequently and we solve more rational equations, there's also something we tend to need to do first before we even get into all this. All of this work I've done and shown here is based off of a premise. And the premise is that 2x over x plus 7 as well as 5 over x plus 1 both exist. That's a lot to say. I'm assuming existence beforehand. Anytime I have to make an assumption like that, if I have to assume that that both of these expressions produce values that exist, and there is going to be a possibility that they're going to exist and have the same value, those are some major assumptions. And when I make those kind of assumptions, that's what causes there to be the possibility for extraneous solutions. For these to exist, the original functions, x could not equal negative 7. And x could not equal negative 1. Those would be solutions that I cannot have, because if x were to equal negative 7, the left-hand side of this equation would not have existed. If x were to equal negative 1, the right-hand side of that equation would not have existed. But when I go through this process and I end up turning this rational equation into basically a quadratic equation, which has no restrictions at all, these solutions could be possibly come out of the quadratic version of this. And because of that, that's where the extraneous solutions would possibly come from. And therefore, there will be times when you solve equations like this and you get your answers down here, you may find out, well, wait a minute, one of these, these answers here don't agree with the answer what I have up there. This one does. Neither one of these is negative 7 or negative 1. These are both credible solutions. I should still probably go back and plug them in to make sure they work. Plugging 5 in, I get 10 over 12 on one side. I get 5 over 6 on the other. Well, 10 over 12 equals 5 over 6. Those are the same fraction. And I can do the same thing with the negative 3.5, which I'm not going to get into right now. So those can be done and verified that those are solutions as well. But, if I had to, if I end up getting a solution that went against this, I'd have to throw it out. So that's where the extraneous solution comes from, because as I work on this equation and I go through the solution process, every step along the way after this, after the initial equation, I'm assuming that both sides of this equation existed. That's a big assumption, in this case, because there are instances where any one of these two sides don't exist. B, slightly more challenging. The reason why B is slightly more challenging is because I am not ready at this stage to handle cross multiplication. I don't have a single fraction on one side equaling a single fraction on the other. I do have a single fraction on the right. That's good. I do not have a single fraction on the left. So for me to get a single fraction on the left, I have to find common denominators. So, and one of the things when you deal with these, don't be in such a hurry to necessarily multiply things out right away, because if you do, you're going to end up getting functions that might go beyond quadratic. So, if you're getting things that have x cubed showing up, or x to the fourth power, x to the fifth power showing up, those are going to be on the nasty side, and you're going to have some issues with that. What I'm going to suggest to you, that if you start seeing those show up and you're trying to solve an equation where you have an x to the third or higher, you might want to consider maybe doing some other manipulations to make that not happen. And it is possible in many cases. But for this one here, I want to try to get, a single fraction to be on the left so I can cross multiply with the one that's on the right. So I'm going to look at these two. This one has a denominator that's actually 3 times x plus 2 minus 1 over. And in these, this is where it comes handy to be able to do some factoring. Now, differences of squares, if I have a difference of squares, and this goes back to, again, some of this factoring stuff are things that, we're assuming you do come into this course having had in the past in previous algebra courses, and that you remember them somewhat. Difference of squares tend to be a situation that's easy to factor. And you're going to see them come up enough, and there are going to be situations that you should also be able to factor. Generally, if you have something that's x squared minus a squared, where you have the difference of two perfect squares, I'm just going to have x, a, and a, basically the square root of each one of those terms. One's going to have the plus, and one's going to have a minus. So x squared minus 4 squared is going to be x plus 2 times x minus 2. For me to get the left-hand side to be something I can make into a single fraction, I'm going to need to be able to carry through that subtraction. For me to carry through the subtraction, I need a common denominator. So when I look at this, both denominators have an x plus 2 in common. I can see that. However, the one has an x minus 2, while the other one doesn't. The other one has a constant of 3 being multiplied, while the other one doesn't. So for me to get a common denominator, I'm going to multiply this by 3 over 3 to get the 3 times the multiplication of 3 down here. This one I'm going to multiply by x minus 2 over x minus 2. And so what that's going to give me is I'm going to have x minus 2 over 3 x plus 2 x minus 2 minus 3 over 3 times x plus 2 x minus 2, which equals 3 over x plus 2. I haven't done anything to the right-hand side because I already have a single fraction over there. Now I have a common denominator I can carry through the subtraction. So x minus 2 minus 3 for the numerators is going to be x minus 5. 3 times x plus 2, x minus 2. So now I have it set up. Now I have a single fraction on the left, and I have a single fraction on the right. Now I can carry through the multiplication, the cross multiplication. So I'm going to go with this crisscross. I'm going to have x minus 5 times x plus 2. And that's going to equal, and when I do this crisscross, I'm going to have 3 times 3 x plus 2, x minus 2. So now I'm going to carry through the multiplications. So on this, on the left-hand side, I'm going to carry through the foiling, and I'm going to simplify as I move along. So I'm going to maybe skip a step as we do this, but make sure you can confirm that you get to the same point. I'm going to have x squared minus 3x minus 10. Here I'm going to have 9. X plus 2 times x minus 2 is kind of reversing what I had up here for the difference of squares. That's going to be x squared minus 4. So now I have x squared minus 3x minus 10 equals 9x squared minus 36. I have a quadratic equation here. I do want to get it, solved. So I'm going to set this equal to 0 because, again, I like the quadratic formula because it's the easiest, and I'm pretty good at factoring and recognizing whether or not it's going to have factors or not. So I can usually do that pretty easily, whereas completing the square, although I know how to do it, it usually has much more heinous numbers to deal with. This is going to have a leading term that's not 1, which causes even more headaches, so I'm not going to give myself the complication of that. So I'm going to subtract the x squared from this side and this side. I'm going to add the 3x to both sides. And I'm going to add the 10 to both sides. And what that's going to do for me is, now I'm going to rewrite everything on the left-hand side with the x's. I'm going to have 8x squared minus 33, or plus 3x minus 26. And that's set equal to 0. With the quadratic formula, I'm going to say, well, x is going to equal negative 3 plus or minus the square root of 3 squared, which is 9, minus 4 times a, which is 8, times c, which is negative 26, all over 2 times 8, which is 16. So 9 minus 4 times 8 times a negative 26 is 841 over 16. The square root of 841 is 29. So x is going to equal, well, negative 3 plus 29 is going to be a 26 over 16, which would become basically 13 over 8, which is the same thing as 1.625. The other answer is going to be, well, negative 3 minus 29 is a negative 32 divided by 16, which is negative 2. But wait. These are the two solutions I have, but again, all this work that I did, every bit of it was working under the assumption that each of the 3 original rational expressions were producing values that exist. And the fact of the matter is there are some values of x where that would not have happened. For instance, when I go back up to here and look at the originals, 3x plus 6, if x equal negative 2, write my pen, if x equal negative 2, the first fraction wouldn't exist. Neither would the one on the right-hand side. Neither would the second function. I mean, the second expression, 1 over x squared minus 4, would not have existed if x equals negative 2. Also, x couldn't be a positive 2 because that would cause this fraction here to also not exist in that instance. So for me to do all this work, I had to have been working under the premise that these were existing, which meant it couldn't be any of these two values. Why is that important? Because x equaling a -2 was one of the solutions I came up with. And although I said I was going to be dealing with that more in a later example, it came up here. This is what we would call an extraneous solution. Now, as we deal with radical equations, we're going to use this idea of the principle of powers along the way. So basically, if I know I have, two things being equal to each other, if I raise them to a power, it's also going to be equal. So if I know that the square root of a plus 9 equals a positive 4. Now, first of all, one of the things to be on the lookout for a possibility of extraneous solutions, and it does come up every once in a while. Remember that a radical, a square root symbol, means the positive square root only. So if I have a radical equation set equal to a number that's not positive, automatically there I'm going to say, well, there is no real solution for this. I just have to stop right there. So, because I'm not going to be able to apply really this radical and be able to come up with a negative answer, unless I'm talking about non-real numbers. But again, when I'm dealing with radical equations, where the assumption is we are dealing with real numbers only. The reason why it's important to have that principle up there is that's how I mainly am going to solve radical equations, because to get rid of a square root symbol like that, I have to square both sides. And when I square both sides, I'm going to have a plus 9 equaling 16, and then I'm going to subtract 9 from both sides, and I'm going to get that a equals 7. Pretty straightforward, and it does work. However, we talked about radical functions before and things of that nature. All this work I just shown, even though it wasn't a whole lot of it, works under the premise that both sides of this equation exist. 4 exists, that's easy. It's a number, we know it's defined, we know what it is. The square root of a plus 9, however, doesn't always exist. There are values of a that makes it not exist. So when I start the problem, or when I realize that once I got an answer, I have to realize that all of this work done was working under a premise that, in this case, a had to be greater than or equal to -9. Because if it wasn't, the square root would have a negative underneath of it, and I wouldn't be able to solve it in the real number system. For the reason that, whereas with the rational equations, I would have maybe 1 or 2 numbers for which it didn't work, or possible extraneous solutions, radical equations have intervals of numbers that won't work. Anything, anything that's under -9 is not going to be an answer. And so if it comes up, which it didn't here, but if it came up, I had to get rid of it immediately. It has to go away. So that's why radical equations will often have situations that have extraneous solutions as well, because for me to carry through the work means that I'm assuming that it's anything but any number that makes any of these radicals not work. Situations where you have a square root of some quantity equaling a number, they're typically going to be very safe. You're not going to really have any extraneous solutions on them. When you get to situations like B and C, that's where they start becoming more of a possibility. Case in point, the square root of 7x plus 4 equals x plus 2. Now I have an x that's not underneath of a radical, and I have an x that is underneath of a radical. I can't combine them in any way. I can't subtract x from both sides or anything like that and make the combine with what's under here, because all of this is basically assumed to be under a grouping symbol. This is also acting as a parenthesis. And we all know that parenthesis, I can't move anything from outside of a parenthesis inside unless it's all I have is a parenthesis. This square root would have to have been dealt with and taken care of and made to go away before I can even possibly combine any terms and things of that nature. So now the thing is here, we're working under a premise that, this is possible, okay? 7x plus 4 has to be greater than or equal to 0 for this to have any kind of solution that I could possibly find. Which means that 7x has to be greater than or equal to negative 4, which means x has to be greater than or equal to negative 4/7. Anything that's under 4/7 will not be an acceptable answer. But I am going to use the fact now that I'm just going to work under the assumption here that, this that I'm only considering values of x that could exist. So I'm going to square both sides to get rid of that radical. On the left-hand side, pretty easy. It's 7x plus 4. The right-hand side, and of course the x plus 2 squared, which I showed here, is going to equal x plus 2 times x plus 2. Sorry for the quick edit on that one. So I want to carry through and FOIL that out. So the left-hand side, I'm going to still have 7x plus 4. On this side, I'm going to have x squared plus 4x plus 4. I want to get the set equal to 0 because, again, I don't usually use completing the square a whole lot. I usually use either factoring or the quadratic formula. So I am going to subtract 7x from both sides and then subtract 4 from both sides. So I'm going to subtract the 7x. That's the two terms that I'll combine. I can subtract the 4. And so I end up with an equation that is x squared minus 3x. The 4 and negative 4 cancel. That's going to be set equal to 0. I'm going to actually use factoring for this because without a c term, it's pretty easy. I'm going to factor out the x. X times x minus 3 equals 0, which means x is going to equal 0, or x minus 3 is going to equal 0, which means x is going to equal 3. So my two solutions are x equals 0 or x equals 3, because both of them fit into this. They're both greater than or equal to negative 4/7. And that works. It makes this, all true. If I had a value that was like negative and below negative 4/7, I'd have to have thrown it out. So moving on to the next one. Here I have two separate radicals being added together, and I'm saying they're equal to 9. I'm not able to combine them through addition. If there was multiplication, I could make that the square root of x plus 7 times x plus 6, or the square root of x plus 7 times x plus 16, but I wouldn't be able to do that through addition. I want to clear out those radicals. It's going to be a little bit more problematic because of the fact that, really the only thing I could do to this to get rid of radicals is to square, but sometimes students, they square this incorrectly, because when I square both sides of this, I'm squaring two terms over here and one term over here. So the right-hand side is pretty easy. The left-hand side, I have to think of it as I'm doing x plus the square root of x plus 7 plus the square root of x plus 16 times the square root of x plus 7 times, getting a little ahead of myself there, plus the square root of x plus 16. And so I'm going to need to do these two together, multiply those. And that the square root of x plus 7 times the square root of x plus 7 is like squaring a square root, so I'm going to end up with x plus 7. The square root of x plus 7 times the square root of x plus 16 is going to give me plus square root of x plus 7, square root of x plus 16. The square root of x plus 16 times the square root of x plus 7 is going to give me another square root of x plus 7, square root of x plus 16. And of course, square root of x plus 16 times the square root of x plus 16 is like squaring that square root. So I'm going to have x plus 16. And that all equals 81. So I'm going to have 2x plus 23 plus 2 times square root of x plus 7 square root of x plus 16. So the issue, compared to the other two times when I squared both sides of the equation, that was enough for me to get rid of the radicals. Here, squaring both sides, I still have terms with radicals in them. So I have to account for that. I got to figure out a way to undo this. So I'm going to subtract 2x from both sides and subtract 23 from both sides. So I'm going to have 2 times the square root of x plus 7 square root of x plus 16 equaling a negative 2x plus 58. Going back to some rules that we learned before, let's divide both sides by 2 because both terms on the right hand side are also even, so I could do that. So I'm going to have the square root of x plus 7 times the square root of x plus 6. It's going to be negative x plus 29. And recognizing the fact that if I have two separate square roots being multiplied together, I can rewrite that as the square root of their product. There should still be a 16 up here. So we have that. I still have that radical, but now when I square both sides and do a second squaring, the radicals will now finally go away. So sometimes you might have to do more than one squaring. Of course, you have to manipulate it so that as you do it, the radicals will eventually disappear. So for this, I'm going to have that x plus 7 times x plus 16 equaling negative x plus 29 negative x plus 29. And so when I work this out, I'm going to have x squared plus 23x plus whatever 7 times 16 is, 112. Negative x times negative x is x squared. Negative 29x, negative 29x is going to be a minus 58x. And 29 times 29 is going to be 841. So I do have a quadratic equation, but as I go through any steps to try to get anything I need on the same side, I mean, ultimately I want my x squareds on the same side. And when I do that, I'm going to be subtracting x squared from both sides to make that happen. They just disappear. So this becomes more of a linear equation. I'm going to add 58x to both sides. And that's going to give me 81x plus 112 equals 841. Subtracting 112 from both sides, I get 729. And dividing both sides by 81, I get 9. So x equals 9. Now again, I have to be careful as I do this. I'm going to pan out a little bit. I don't want to move that. All of this work I had done, again, was working under the assumption that both of these radicals existed. And for that to be the case, for the first one to work, let's do orange here. For the first radical to work, x had to be greater than or equal to -7. And for the second one to work, x had to be greater than or equal to -16. I don't have to really stay this part here because if x is greater than or equal to -7, it has to be greater than or equal to -16. So this has to be the case, which 9 falls into that category, so we're good for this. But I always have to make sure to check back to make sure that whatever answer I'm coming up with isn't having some sort of fault with the original functions and isn't producing something that doesn't exist. So that's where we get into example 2 now, or example 3, which we deal with extraneous solutions. So let's have a look at them. Now these are going to pop up some extraneous solutions, but there's different ways to determine them and figure them out. There we go. So A is obviously a rational equation. I want to start this off by saying, okay, well, before I start making determinations about like what are my possible domain restrictions, I'm going to factor anything I could possibly factor, which on the left-hand side, really not much to do. Although I don't want to write a plus sign where there's a minus sign. That would certainly throw me off a bit. So minus 4 times x over x plus 4 equals 32 over x squared minus 16. I don't want to rewrite that. X squared minus 16 is a difference of squares, so that's going to be an x plus 4, x minus 4. It's important to have those because identifying those makes it easy to identify what's going to cause some potential issues. Obviously, if x were to be 4 or -4, it's going to make, I mean, each one's going to make 2 of these 3 rational expressions become a quantity over 0. And I can't have that. So I have to work under the premise here that x is not equal to 4 and x is not equal to -4. Keeping that in mind now, I'm going to work under the premise that is the case, so I want to carry through the work I need to do to solve this. Now, again, when I'm dealing with rational equations, my goal is to be able to eventually cross-multiply. Can't really cross-multiply here yet because I need to have a single fraction on one side and a single fraction on the other. I have a single fraction on the right-hand side, a single rational expression. On the left-hand side, though, I have the subtraction of 2 rational expressions. So I got to carry through that subtraction, and for that to happen, I have to get common denominators. And under most circumstances, I'm just going to take the 2 denominators I see here and multiply the tops and bottoms by those. I'm kind of squishing it in here. And so the left-hand side is going to become x times x plus 4 over x plus 4 x minus 4 minus 4 times x minus 4 over x plus 4 x minus 4, which equals 32 over x plus 4 x minus 4. So on the left-hand side, I have essentially x squared plus 4x minus 4x plus 16 over x plus 4 x minus 4. And that's me doing several pieces of work all at once. I'm distributing the x here. That gives me the x squared plus 4x. I'm distributing the negative 4 here, the minus 4, so it's negative 4 times x is a minus 4x. Negative 4 times negative 4 is a plus 16. I didn't combine any like terms, although if I can, these x's would disappear. So I'm here. Now, as I said, I could just automatically cancel these because they will. So I essentially just have x squared plus 16 on top. The only way for this to be a true case, now I could do some cross multiplying if I want to. However, if I do cross multiplication and multiply it through, I'm going to have a fourth degree expression on one side of this equation when I do that. Because x squared plus 16 times x plus 4 times x minus 4 is going to give me a fourth degree polynomial, which we haven't gotten into how to solve those yet. So, I don't want to go that route because I don't know how to handle those. But I can also use the fact that I have x squared plus 16 over the same denominator as 32. If they're both being divided by the same thing, that means that the tops have to be equal to each other. So I have to work under the premise now that x squared plus 16 would have to equal 32. Makes sense. And so x squared is going to be 16 when I subtract both sides by 16. And when I square root both sides, remember the plus or minus here, I get that x equals 4 or x equals negative 4, which unfortunately are the two conditions I said, well, I can't have that happen. Those cannot be the case. Therefore, both of these are extraneous, which implies there is no real solution. So that works out pretty neatly, so for B, now I'm going to show you a couple ways of handling it. One, you can, if you're paying attention, will make it known right away based on something I mentioned before in this video. For me to start going through the process of solving this equation, first of all, I'm going to take note of the fact that A is going to have to be greater than or equal to negative 4, first off. Because that would make the radical portion of this not exist if it didn't meet this condition. So I had to work under that premise. I'm going to subtract 7 from both sides. And I get this. Now at this point, you could stop right here and say no real solution. Because the square root of a plus 4 needs to be greater than or equal to 0. The square root of anything should be positive or 0. Because it's a principal square root. It means only the positive square root. A positive square root's not going to give you a negative value unless you have a non-real answer. I'm not looking for non-real answers. So I could say no real solution right there. But say you didn't notice, say you weren't paying attention, and you didn't notice that you're saying the positive square root of something equals a negative number. You will eventually be able to make the same conclusion as you proceed through this. So let's continue this as if we didn't notice that. I would of course then square both sides to get rid of the radical. And that gives me a plus 4 equals 16. And that means that a would have to be 12. And you're saying, well, wait a second, Mr. Sorrentino. This is a number. It's certainly greater than or equal to negative 4. What's wrong with it? Well, here's what's wrong with it. I'm going to go back to the original equation. I should always be doing this anyway. I should be checking my work on any equation I solve to make sure that the answer I get works. if I do the square root of a, which is now we're saying is 12, plus 4 plus 7, if it's an answer, it should equal 3. Well, 12 plus 4 is 16. The square root of that is 4. Does 4 plus 7 equal 3? Well, no. 4 plus 7 is 11. So that doesn't work. So this is extraneous because it simply doesn't work. That happens very frequently with radical equations as well. Um, I'll get solutions that algebraically are sound, but when I go back and check them, they just don't work. They don't cause a domain restriction or an issue like that. They just don't work. And that's what happens here. So, if I only get one solution and I say it's extraneous, that would give me the same realization that there is no real solution. So, there's different ways to come to that conclusion in this type of problem, and that's how you go about doing it. The last examples that you have deal with situations that are a little bit more abstract. And all they're asking you to do is solve the equations for the indicated variable. Now here I don't have to worry so much about domain restrictions and things like that because I don't know what any of these are. So we're still working under the premise that these things are all existing, and that these expressions and combinations are existing. But I can't restrict it and say like it's not when it's going to work and not going to work unless I know more about these numbers. So let's have a look at that last example 4. So here we're just looking to solve the equation for an indicated variable. Right now this equation is solved for c. C is alone on one side of this equation. I want to get it so it's solved for b, this one right here. So I got to think about, well, I want this to look like eventually b equals something on this side. That means that b should be alone on one side of this equation in the numerator. So when I look at this, I say, well, what do I need to do to carry this out? I can think of the right-hand side as being c over 1. And that allows me to cross multiply. So I can say that d equals acx plus bcy. At least now I have the variable I want in the numerator. I want this b to be the one that's alone. So I got to think, well, I have a cy being multiplied to it, and cy itself is a multiplication, and I have an acx being added to that b. So if I'm following my order of operations in reverse, I get rid of any additions to subtractions first. So I'm going to subtract acx from both sides. And what that's going to leave me with is I'm going to have d minus acx equaling b times cy. And I'm writing it this way only because of the fact I want to kind of emphasize the fact that cy is in total is being multiplied to b. And that kind of lets me know what I need to do to get b alone. I need to divide both sides by cy. And what that's going to give me now, because these would cancel, is that b is going to equal d minus acx over cy. And that's the expression I want to get. For b, I want to solve this for p. I want to get, so basically I want this one right here to be alone on one side. So I want p to equal something when all is said and done. So let's work on trying to do this. Trying to get p in the numerator right now is a little complicated because right now I have a fraction involving p being added to another fraction. If I try to do anything right now that puts p in the numerator, or I try to combine the terms I have over there, I'm going to start creating more variable p's, and I certainly don't want to do that because that goes in the opposite direction. I mean, I don't want to create more of the same variable if I'm trying to get it down to just one being left alone. So what I'm going to do to start this one off is I'm going to subtract 1 over m from both sides. When I have variables in the denominator, I try to do some sort of cross multiplication, which I can only do if I have a single fraction on both sides of the equal sign. I have it on the 1 over p side. I have two fractions being subtracted on the other side. So I got to carry through the subtraction, which means I need to establish some common denominators. So I'm going to multiply this one by m over m, and this one by f over f. And what that's going to give me is I'm going to have m over mf minus f over mf equaling 1 over p, which means I'm going to have m minus f over mf equaling 1 over p. I could cross multiply and give myself more work to do, but it stands to reason that since p and 1 over p are reciprocals, then, p should equal the reciprocal of this side. So I'm going to have mf over m minus f, and that solves the equation for p. And that's the end of it. Now, up to this point, we've worked with rational equations and learned how to solve them. One of the things that we always look to with those is that there was always complications involving domain restrictions. And we're going to see how that domain restriction gets handled here. We're also going to talk about these functions in a little bit more detail because oftentimes when there's domain restrictions, there's also range restrictions as well. And we're going to talk about those as well. In particular, in this section, we're going to learn how to create their graphs, again, accurately without hopefully having to plot a whole lot of. So a rational function is made up basically of the division of two polynomial functions, and that's what its official definition is. It's basically we have the division of two functions where those two functions are polynomial functions. When we have a polynomial function in the denominator, which means we probably have at least one variable of x in there, we run into a potential to have a situation where q of x would equal 0. But the thing is, that is something we don't want, because that means for that particular value of x, this new function that's the result of dividing these two other functions doesn't exist. So what we have to be keeping in mind is that we do have domain restrictions of rational functions. It's any value of x where q or 0 is where x is a 0 of q of x. So we want q of x to not equal 0. Well, these domain restrictions, any of these places where the bottom function becomes 0, which makes the whole function undefined. There's two different phenomena that happen with these kind of graphs of rational functions that happen because of domain restrictions. I can either have what is known as a vertical asymptote, or I can have a hole. Just for a side note, in calculus, they may refer to these as a vertical asymptote would be an infinite discontinuity, and the hole is sometimes referred to as a removable discontinuity. The reason it's important to kind of note this, more so for the hole, is because its name, removable discontinuity, kind of lets us know whether or not we have a hole or not, because a removable discontinuity implies that we have a cancellation. We have a cancellation that's possible that would simplify the function. Now, when I simplify, and although the cancellation can happen, which makes it easier to graph, easier to calculate things, I have to keep in mind, though, that the cancellation does not mean that we forget about the domain restriction. It just means that we have to account for it as being a whole. So let's see how we could identify what these are. So let's have a look at example 1. And example 1, 2, and 3 are basically the same 4 functions. We're just looking for different parts of them. And to eventually, in example 3, we could write a graph of the function. So that's what we're looking to do here. So in example 1, we're just going to try to identify any vertical asymptotes or holes in it. So let's have a look at example 1 and start this process. So for these first 2 functions, looking at a first, it's a pretty simplistic function here. I can say by looking at it, well, obviously x cannot equal a negative 4. Because that would cause there to be a 0 in the denominator. This is a domain restriction. Now, is this a vertical asymptote or a hole? Well, how I make the decision is, okay, I look at this and say, well, is there any way for that, the thing that causes this domain restriction is me having this x plus 4 in the denominator. Is there any way for me to cancel out this x plus 4? Is there anything on top that I can cancel it with? I just have a number 2 up there, so no. There's no cancellation possible. And since there's no cancellation possible, x equals negative 4 is a vertical asymptote. That means whenever I eventually do a graph, I'm just going to do a really quick rendition of one right here. Here's my graphing region. And say here's negative 4. I'll usually will indicate that by putting some sort of vertical line in there to indicate that that's a vertical line that the graph can approach infinitely but never cross. In vertical asymptotes, they can never cross. So we talk about horizontal and oblique asymptotes as we move on to this. That's a different story. So let's look at g of x. G of x, now whether I factor the bottom or not, I could probably figure out what values of x would make the bottom 0. But just for the sake of argument, and this also helps for the discussion we're doing here, I can factor the bottom into x plus 3, x minus 3. And I'm just going to put a parenthesis up here as well. So my domain restrictions are that x cannot equal negative 3, because that's going to create a 0 with that one. And x is not equal to 3, because that'll make this one a 0. So I have 2 domain restrictions here. But what kind of domain restrictions are these? Well, if I look at the function that I have in front of me, once in the factored form, I can see that the top has an x plus 3 being multiplied essentially to 1, and I have an x plus 3 on the bottom being multiplied to x minus 3. That means that I can cause a cancellation. That cancellation means that g of x is approximately equal to 1 over x minus 3. And if you would graph x plus 3 over x squared minus 9 and 1 over x minus 3, you would see on a calculator or a computer, you would see exactly the same thing. The reason being that there is a difference between them because of the fact that, this function here has no issue with x equaling negative 3. And that purple version of g of x equals negative 3 is perfectly allowable. The problem is it's not allowable in the original function. So these are so there would be a hole here. And that's basically what caused here the x plus 3 would cause the issue with the negative 3 being an issue, a domain restriction, has been removed. Hence the name removable discontinuity. Therefore, I can say I have a hole. Now, a hole is going to be a set of coordinates. I can't just say I have a hole at x equals negative 3. I know that negative 3 is going to be the x value. because x cannot be negative 3. Now, to figure out the y coordinate that goes here, I'm going to just simply do g of negative 3 on the purple version. And I do 1 over negative 3 minus 3, which ends up being a negative 1/6. And so I have the location of the hole. Whereas, since the x equals 3 is still an issue in the simplified form, I'll say this is just the simplified form, it's still an issue in there. That indicates that is a vertical asymptote. So I have a vertical asymptote equals positive 3. And that's how I make the determination. A cancellation, once I determine what are my domain restrictions, if the cancellation eliminates one of those domain restrictions, that becomes a hole. If once I cancel, if there is no cancellation I can do, the domain restriction I noted before is still a problem, then it is going to be a vertical asymptote. So this one would have a hole and a vertical asymptote. And we'll show later how to graph them and deal with those when we get to that point of graphing them. On to C. As before, for me to find domain restrictions, it's usually a good idea for me to factor the top and bottom. Now these are going to be factorable. You may want to go and use the AC method. I'm not going to show the entire AC method here for the sake of time for this. But the top would factor into 4x, this would be x, this would be a 4 minus and a plus 1. So 4x plus 1 and x minus 4. Down here, the bottom would factor into 2x minus 3 and x minus 4. So with this in mind, I could easily identify what the domain restrictions are. X cannot equal 3/2 or 1.5 because that's going to create an issue in the first one. And x cannot equal 4 because that's going to cause an issue in the second quantity I have in the denominator. Well, when I look at these functions, h of x can be rewritten or simplified, and I'll just say it's a simplified version. The x minus 4s would cancel. I have the 4x plus 1 and the 2x minus 3. So the fact that the x minus 4 is canceled, and those are the issues that cause me to have x equaling 4 as a domain restriction to begin with, that indicates that I have a hole where that x equals 4. Of course, I have to do a side problem down here. I gotta say, okay, well, what's h of 4? And I could do that in the simplified version because, if I try to put it in the original version, obviously I'm going to get 0 over 0, which is not anything. The simplified version of this becomes 17 over 5. And 17 over 5 is equal to 3.4. So I'm going to have a hole at 4, comma 3.4. And because the 3/2 stays, the 3/2 is still going to be an issue in this one down here, I could say that I have a vertical asymptote at x equals 3/2. So we have these two. This one also had a hole and a vertical asymptote, and that's how we handled it. In the last one, I have j of x. I have j of x equaling 2x cubed minus 4x squared over x squared minus 4x plus 4. Well, if you go through and factor the top and bottom, because we want to factor the top to see if there's any potential cancellations, we factor the bottom to determine, what my domain restrictions are. X squared minus 4x plus 4 is actually x minus 2 times x minus 2. I can write that as x minus 2 squared, but for the time being, I'm just going to write it like this. The top factors into 2x squared times x minus 2. So there is my factored form, more or less, of j of x. And I can see here I really only have one domain restriction. X cannot be equal to 2 because that's going to create 0 in the denominator. That's the only number that's going to make a 0 in the denominator. Well, I see that both of them have a multiplication of x minus 2 on the top and bottom. I mean, the bottom actually has 2 of them. So when I do my simplified form, now I only have one domain restriction. It has to be either a hole, also known as a removable discontinuity, or a vertical asymptote. Well, which one is it? Well, it's still the same rule. Yes, I canceled out an x minus 2, which is what creates 2 being an issue with this. The problem is, I still have x minus 2 down here. X minus 2 still means that 2 is an issue. And since after my cancellation, after I simplified, I still have the same issue, that means that it's going to be a vertical asymptote here. So I'm going to have, there's only one feature that the domain restrictions cause here. It's going to be a vertical asymptote at x equals 2. And so that takes care of finding vertical asymptotes in holes. You know, you're not guaranteed to have either, but you have to know how to search for them. The next feature that rational functions will have are horizontal or oblique asymptotes. And so let's take a look and see how we can determine those. So for this, in this course, you're gonna have to just get to know some rules to help you with the horizontal or oblique asymptotes. We look at the degrees of the two functions that make up the rational function. N is the degree of the numerator, m is the degree for the denominator. If the degree for the numerator is smaller than the degree for the denominator, then we have a horizontal asymptote at y equals 0. If they're equal to each other, if I find the highest power of x on top, find the highest power of x on the bottom, and see that they're the same degree, then what I do is I take a ratio of the leading coefficients. Again, I have to make sure I identify the leading coefficients correctly, because sometimes you might be given functions on the numerator and denominator that are not written in standard form. Please make sure you know the leading coefficient does not mean the first coefficient you see. It's the one attached to the highest power of x, and also make sure that you're aware of the signage of those. And lastly, if n is greater than m, then the function has an oblique asymptote found by finding the quotient of f of x. I'm going to say here minus the remainder. Oblique asymptote simply means, you know, for our purposes in this course, slanted line. Oblique asymptotes can have many different shapes. They don't have to be linear. They could be other shapes. They could be parabolic. I mean, there's a whole bunch of different shapes they could possibly have. For our purposes, they're only going to be slanted lines. So, you know, I'm going to have a vertical asymptote for sure, or a lot of cases. I'm either going to have a horizontal asymptote in these two cases, or I'm going to have an oblique asymptote in the case where the degree on top is higher than the degree on the bottom. Another thing I want to note before we get into actually doing the problems here is that these types of asymptotes, horizontal and oblique asymptotes, are end behaviors. An asymptote is basically, in many cases, a line that a graph approaches infinitely, gets infinitely close to, but never crosses. For horizontal and oblique asymptotes, that's not exactly as true. As you go out like towards the ends, you go to negative infinity or positive infinity, yeah, that's the way it's going to behave. But when all the interesting stuff happens towards the middle of the graph, it is possible to have situations where a graph of a rational function may in fact cross through the horizontal or oblique asymptote. That's why if you have a horizontal asymptote, could possibly have a range restriction, or you may not. You just have to see how it plays out. This happens more often when you have multiple vertical asymptotes, or situations like we had in D where we had a cancellation of the x minus 2, but yet it still remained there. Sometimes those kind of things cause, situations where the graph might pass through the horizontal or oblique asymptote, but doesn't necessarily mean it's going to avoid it completely. It's only going to do so towards the ends. So let's look at the situations for example 2, these first two. Now, it's for vertical asymptotes and holes, it's good to have these, factored. For the purposes of finding horizontal or oblique asymptotes, it's good to have them the way they are. Okay? That's not to say that if we go back and look at what we've done for the vertical asymptotes and holes and the work we did to identify those, sometimes using the simplified version is okay too. So I'm going to put that up here, and we'll look into that and explain why momentarily. But ultimately you want to be able to look at the functions and say, okay, well, what's going on with your highest powers of x and so forth. So for instance, in f of x, this is degree 0. I don't have any powers of x here. This is degree 0. The bottom is degree 1. So I have a situation where my numerator's degree is smaller than my denominator's degree. That's a pretty simplistic conclusion. I have a horizontal asymptote at y equals 0. If you think about it, in this particular function, since the top would remain 2, and the bottom, if I put bigger and bigger numbers in for x, I'm going to get bigger and bigger denominators. If I have a fraction where the numerator stays the same and the denominator just keeps getting bigger and bigger, the overall value of that fraction becomes closer and closer to 0. And that's what the asymptote is indicating. It means I'm getting really close to 0, but technically I'm never really going to touch it. I mean, I can have 2 over 3 trillion. That's going to be very close to 0, but it's not equal to 0. And the same thing if I pick really large negative numbers, I'm going to get a really large negative number in the denominator. The only thing that's going to be different is when I carry through that division, I'm going to have a really, really small decimal, but it's going to be negative. It's still getting closer to 0, but it's never going to actually equal it. So that's the reason why it ends up being that. It's pretty easy to see in this one. For the next one, it's the same issue. Up here, I have a degree 1 polynomial. Down here, I have degree 2. If you remember, we also said that the simplified version was 1 over x minus 3. If I look at the simplified version, it's the same thing. I have a 1 on top, and I have something on the bottom that could get really, really big if x is really, really big, which means I'm getting closer to 0. Or it could be really, really, really negative, but large value negative, which means in both cases, the fraction's approaching a value of 0. B has a horizontal asymptote at y equals 0 as well. Moving on to C and D. In C and D, for C and D, h of x, I can see here the top is degree 2, the bottom's degree 2. I'm going to have a horizontal asymptote. The thing is, I have to come up with what that horizontal asymptote is going to be. Well, according to the rules we discussed before we got into this example, it's going to be a ratio of the leading coefficients. So, since the x squared is the highest power of x on top, 4 is the leading coefficient. X squared is the highest degree on the bottom, so 2 is the leading coefficient. So, this is going to be 4 over 2. So y equals 2 is the horizontal asymptote. Lastly, is degree 3. The bottom is degree 2. Once the power on top is larger than the highest power of x on the bottom, I know I'm going to have an oblique asymptote. Now what I have to do is going to be y equals, well, I have to come up with the formula for, in this case, it's going to be a line. Well, where is that going to come from? Well, what I do is simply carry out the division that I see. So, and since the bottom is in fact x squared minus 4x plus 4, I'm going to carry through that division with that. So I'm going to use long division. So I'm going to take the 2x cubed minus 4x squared plus 0x plus 0. Remember, I have to put any missing powers of x into it that aren't in them. And I'm dividing by x squared minus 4x plus 4. And I'm going to carry through the long division here. I carry through the division all the way, even though I know that once I brought down the plus 0, whatever I would divide out, once I carry through the division, anything left would be the remainder. I really don't care about the remainder. It's really just this part right here that concerns me. That is going to be what the formula for the oblique asymptote is going to be. It's going to be the 2x plus 4, which of course would be a slanted line. It's in slope-intercept form, and you should be able to graph that. So this is the information I have gathered so far. So far I have found any and all vertical asymptotes and holes. I have found whether or not it has horizontal or oblique asymptotes for each of these, and then discovered what it is. Now I'm ready to graph. So let's look at the graphs for these, and that's what example 3 is. So here we are at example 3, and as you will notice, as I start example 3, I just transferred the information that we had figured out and determined from examples 1 and 2 for these 4 functions. So we have this information here. For A, all I really have are the vertical asymptote and the horizontal asymptote equations. So, I'm going to graph them, but usually when we graph them, if you're using a pencil, you should be like either writing it, drawing it like lightly, or sometimes we use dashed lines. For the purposes of this video and using this feature here, I'm going to use a highlighter, essentially. So x equals -4 and y equals 0 is here. So those are my asymptotes, okay? They're not part of the graph, which is why we draw them dashed or lightly, or in this case I'm using highlighters, because they help us determine the shape of the graph. They really are not part of the graph. So the information I have discovered from examples 1 and 2 for this, I don't have any coordinates for this. All I know is that the vertical line x equals -4 is a line that the graph will never cross. The horizontal line y equals 0 is a line that, as it goes on forever and ever, the graph will never cross, but it may cross somewhere else, towards the center. I got to get actual points for this. And so I am going to resort back to coming up with a table of values and plotting them. But at least now with the information that I have, I can be more selective about what that information is, because most of the interesting features of the graph, any twists and turns and bends and things like that, are going to occur around the vertical asymptotes. And if there's more than one, then you have to account for that. But that's where most of the interesting things tend to occur. So I'm going to put the -4 here, indicate it's undefined here because it is a vertical asymptote. But I want to make sure I pick some points that are near the vertical asymptote and some points that are further away. So for instance, I might want to pick -5 and see what goes on with that function there. I maybe want to pick -3 and see what goes on there, because those are pretty close. I can even get closer and use decimals as well, but whatever I put in, these are things I'm going to put in and eventually calculate. So I might want to make them easy at first, and if I see that I might need to put in some decimals, by all means I'll do that. I also see what's going on a little further away from it. So I'll maybe say, okay, I'll find a point at 0 and see what goes on there. And for this one here, maybe say, let's go to -7. So we have some points that we could possibly try out. So basically here, I'm going to plot I'm going to find and plot 4 points, and that should hopefully give me a good enough picture of what's going on, and I can draw it fairly accurately. So if I plug -7 in, I'm going to have a -2/3. Now, depending on how you have your graph scaled, you may have to take some guesses with this. 2 over -5 plus 4 is going to give me a -2. 2 over -3 plus 4 is going to give me a +2. And 2 over 0 plus 4 is going to give me 1/2. So I'm going to plot those points. So the graph overall would look like this. Now, if it looks like you're touching your asymptotes, that's okay. Just don't cross through them unless you see evidence to suggest you should. But generally, that's what the graph is going to look like. And I could even, at this point, get rid of the marks here to make it a little bit more definitive. Because if you graph these on the calculator, 84s, if you have one of those, they're going to tend not to show the asymptotes. 83s may. I know there was some later versions of the operating system that learned to exclude them, but most 83 pluses would graph the vertical asymptote. So just be on the lookout for that. When I go to part B, again, I have minimal information here. I mean, I do actually have one thing that acts as a point, but starting off, I have x equaling 3. Make it a little softer here. X equals 3 as a vertical asymptote. I have y equals 0 as a horizontal asymptote. And I have the point -3, -1/6 as a whole. So -3, -1/6 we'll say is about here-ish. I am going to indicate it with an open circle. So unlike the previous one, I have something that's kind of like a point on the graph because that open circle should lie along the graph. But again, I don't have a whole lot as far as it helping me figure out what the shape looks like. So likewise before, I'm going to set up a table. And again, I'm going to center it around my vertical asymptote. So 3 is going to be kind of where I'm centering it. Of course, that's where y is undefined. And again, I want to pick a value that's maybe closer to 3. When it's a little further away, I always try to incorporate 0 because the zeros are easy to work with. And then maybe one that's that's close but bigger, and one that's maybe a little further away. And what I could do with these now the easy part about this, I can plug them into the original and get the same numbers I'm going to get as if I plug it into the simplified version. So having the simplified version can make a little less work, because this is going to be a -1/3. And if you plug it into either the g of x the way it originally was or the simplified version, you get the same thing. This is going to be a -1. This is going to be a +1. This is going to be a 1/3. So I'm going to plot these points. 0, -1/3, we'll say is about here. 2, -1's about here, is right there. 4, 1 is right here. And 6, 1/3 is about here. So my graph is going to look something like this. And again, I'm able to produce a pretty accurate picture without graphing everything, without having to plot a whole bunch of points. That's the whole gist of doing this. For C, again, I'm going to start with plotting my horizontal and vertical asymptotes as well as the whole. So x equals 3/2. This one I might go with dotted lines because the 3/2 means it's 1.5, so like x equals 3, so the vertical asymptote would be about here. Y equals 2 would be here. This is a line where it could cross in the center, but not necessarily going to. Towards the ends, it definitely should start behaving like a regular asymptote. And of course, I have a point at 4. Again, in the end, I only have one thing that acts as a point. I don't know what the rest of the graph looks like. So I'm going to choose some points. Again, I'm going to let the vertical asymptote be the central feature, because that's where it's undefined. So I'll pick a value that's I'll pick some values that are bigger. So we'll say maybe 2, because that's pretty close by, and one a little further away, so let's say 4. Well, we already know what happens at 4. I could actually use the hole up there as a point, so um, maybe say 5. Just have one more point. Up here I can have 1, I can have 0. That should give me an idea of things look like, and I'm just going to put these values in. So again, I'm looking for, like when you do the graphing parts, I'm looking for some coordinates that you're calculating, some points that are accurately produced. If it's not perfect, that's okay. So we have the vertical asymptote, x equals 2. To show more of the graph, I decided to rescale this and go by 1s on the x-axis still, but go by 2s on the y-axis. So when I still plot x equals 2, it's still going to be here, and I'm going to use dashed lines this time. It's a little some more simplistic of graphing the line if I'm not using a thick marker. And y equals 2x plus 4. Now the careful thing is I have to remember first, plus 4 is here. That's going to just be 2 up. And I have to remember that as I go on these grids, one grid is 2 in the vertical direction, whereas left and right it's 1. So the slope of 2 is going to look like this on this particular graph the way it's been scaled. So you don't have to scale the x and y axes the same way. But at least now I have a little bit more room, like up here, you know, beyond the intersection of the two lines. I mean, that's an important area of the graph. I mean, I have to see what goes on around it. But I mean, I have 4 regions now. I want to be able to see if there's anything that goes on in this region up here. I want to be able to see it. Whereas before, it was kind of it was falling off the graph. I still use the vertical asymptote as a central point. That's where it's undefined. And so I want to pick some values that are close by, maybe one a little further away. Same thing here. And we'll just say negative 2. If I put that in, I'm going to have 8 over negative 4, which is negative 2. So I'm going to plot these points, and that's what that graph would look like. Now this one here is a little bit more challenging. It has some things, I mean, that you have to do much like you had to do with the previous one. However, at the same token, there is some differences in this. That's kind of representing an interesting situation here. So, first what I'm going to do with this, and what you should have done with it, is that I'm going to factor the top. Well, the top doesn't really factor in anything, so it's going to say 2x cubed. The bottom is a difference of squares, so it ends up with x plus 2 and x minus 2. And it's important for me to have that because, now I can say like, well, I have domain restrictions. X cannot equal negative 2 and x cannot equal 2. So if I didn't realize that before from the x squared minus 4, which I could just simply set equal to 0 and solve that way and figure out what these are, I can at least see it now because once I have them factored, I can figure out what makes them 0. Well, as you can see here, there is no division that can be done. So, there's no cancellation it's going to have. So I don't have any holes. There's no holes on this one. But what I do have are 2 vertical asymptotes. So I have vertical asymptotes at both x equals negative 2 and x equals 2. I'm going to go to the graph and put those in a while. Again, it's going to help me figure out some things about the graph later, but right now that doesn't really give me anything on the graph. Now I'm going to look to figure out whether I have horizontal asymptotes or oblique asymptotes and find out what it is. I notice the degree is 3 on top, the degree, going back to the original one in particular, is degree 2. That means I have a higher degree on top than I do on bottom. That tells me I'm going to have an oblique asymptote at y equals, but I got to figure out what that is. So I'm going to go back to the original two numerators and denominators because I really can't do any cancellation. I can't come up with a simplified version. So I'm just going to take the 2x cubed, remembering to represent all the other powers of x. And divide it by the x squared minus 4. Again, remembering to represent any of the missing powers of x I'm not seeing. And I'm going to carry through the long division, so the quotient will eventually be what y equals for the oblique asymptote. So this is the quotient. So y equals 2x is what I'm going to be graphing here. I think I can leave the y grid going by ones, so I'm just going to plot y equals 2x. And so there is my oblique asymptote. Now again, these are just features that the graph is going to avoid in some way. May cross over, may not cross over, but towards the ends of the oblique one should avoid, and certainly the vertical ones will be avoided all the time. This doesn't let me know what's on it. So here's what I need to do. Now, when I have multiple vertical asymptotes, if I'm going to have any situation where my graph crosses my oblique asymptote, it'll probably be occurring between the two asymptotes or pretty darn close to them, so in between the asymptotes, I might want to pick some more points is what I'm getting at, not just say, okay, one close, one far away, when I start mapping out my coordinates I might want to plot here, I want to include the -2 and the 2 for sure. I'm going to indicate them on my little chart here because those are central features of the graph. For the time being, I think -1, 0, and 1 would be good in between. I could put in some fractions if I want to, but it's not necessary. Make sure I have some that are close by here. Maybe go a little further out and even yet a little further out. And same thing here. So I would want to compute all of these. So these are the values that I computed by plugging them in. Some of these don't fit on the graph very well, because I only go up to values of 10. So let me just do a quick rescale of my graph. I'm going to let my y-axis go by 2s. So I'm just going to do a quick changeover. So it's a slope of 1 on this graph, but I have to remember and vertically each grid mark I'm moving is 2. And changing your graph around as you do this and thinking about your scaling are things that you want to do. You want to be in flux until you get something that you can fit the entire picture on. Because I want to be able to put some points on here, and a lot of my points, especially on the left and right of the two vertical asymptotes, the far left and far right, I was losing points. There wasn't anything I could do with them. So let's plot these points now. So there's approximately where the points would go, but knowing about what the graph's doing, I would expect the graph to do something like this. Here, the graph is passing through my oblique asymptote, but I'm going to expect it to do something along the lines of this. And again, if I can verify this by picking some additional points on this. And up here, I expect to do something along the lines of this. And that's what the graph would look like. So I can make some pretty good predictive behaviors with very few points based off of me knowing how things obey vertical asymptotes and things like that. I don't have to get worried about this point right here where it crosses, the oblique asymptote in the middle, because I kind of expect that to happen since that's towards the middle, but towards the ends it starts avoiding the oblique asymptote as it should. And so that's a kind of interesting things that can happen when you have multiple vertical asymptotes. Also, when there's chances for or things cancel, but yet you're still left with the vertical asymptotes, things like that can sometimes happen as well. Didn't happen with one example we did, but it can happen. So be on the lookout for those things, and sometimes you might have to pay a little bit more attention and graph a little bit more detail and pick some more x and y values. Means it's always a good idea to throw this up on your calculator, see what it looks like, and if you're seeing a feature that looks like it's totally different to what you're graphing, you may want to explore into that until you get the hang of knowing what to expect and what to show. But that brings us to the end of this video. If you have any additional questions with this topic, please make sure to bring them up in class or come and see me during my office hours. Until I see you in one of those situations, or until the next video, I will see you around, and have a good day.